Hi there, it's Chris Clements. It's been a long time since I've made a podcast, but I realized I had not posted one that's on gas laws. So we're going to go over some gas laws. It'll be a pretty short one, I would imagine. So let's go ahead and get started. We need to know what pressure is. Pressure is caused when molecules or formula units or atoms collide with a container. The container can be something that is tangible or something that could be our bodies or our homes, a wall, a balloon, any kinds of stuff like that. So I'm not going to go any deeper in that with Chemistry 1, but we go a little deeper in Chemistry 2 with that. So just kind of prepare yourself if you're taking Chemistry 2. Okay, you need to be familiar with some units of pressure. You've heard me say this before, and I told you we'd get to it later, so here we go. You need to be familiar that standard pressure is what we generally feel around here in Shreveport, Louisiana is like, because we're so close to sea level. As you climb upper in altitude, you get less pressure because there are fewer molecules pushing down. So if you're up on top of Pikes Peak, you're going to feel less pressure than what you feel here in Louisiana. Alrighty, so some units that I wish for you to be familiar with are the atmosphere, and standard pressure is 1 atmosphere at our location, basically. So for us, it's pretty much always 1 atmosphere unless a tornado rolls through or a hurricane rolls through. I've got some kitties who are roaming around, by the way. You're liable to hear some meowing or some fighting from them, who knows, but you're liable to hear some clocks as well, just interrupting you there. All right, so 1 atmosphere equals 760 millimeters of mercury, and that's literally measuring a mercury column in the unit of millimeters. In the United States, we tend to not use millimeters of mercury, we use inches of mercury. So 760 millimeters of mercury is the same thing as 1 atmosphere. 29.9 inches of mercury is the same thing as 1 atmosphere. And then a unit that's the same thing as millimeters of mercury is the torr, in honor of a gentleman who did a lot of work with pressure and how we measure it and what we know about it, named Torricelli. And another unit that I think you need to be familiar with is the pounds per square inch. I enjoy sharing that one with you because most of us have some sort of experience with that, with filling up a tire with air. And it says PSI on the side of a tire. So 1 atmosphere equals 14.7 PSI, pounds per square inch, abbreviated with PSI. We're going to go over several laws as I go through this. The first one is Dalton's law. Dalton's law tells us that when we have a mixture of gases, that the total pressure of the mixture of gases is simply a sum of the partial pressure of each gas. And that means that each gas in a mixture of gases creates its own pressure, and all we have to do to figure out the total pressure is add the pressure of each gas together. They're called partial pressures. So for example, air is primarily made of nitrogen, and then next most abundant is oxygen, next most abundant is carbon dioxide, and next most abundant is argon. And all the other gases that happen to enter our air are so minuscule in comparison to those 4 that we just don't even consider them. The next law, it's called Boyle's law. A Scottish gentleman named Robert Boyle studied the relationship between pressure and volume and determined that pressure and volume are indirectly related, which means that as we look at holding a temperature and a number of moles constant, where N represents number of moles and T represents temperature in Kelvin, I'll get to that a little bit later, we can see that pressure and volume vary indirectly. Think about pushing down on a piston. That's what I've illustrated here. If I push down on a piston and make the column of air or whatever gas that's inside it a shorter column, then the pressure is going to go up. I've decreased the volume, but the pressure went up, and vice versa. If I lift up on the piston, the volume goes up, the pressure will go down. In a formula that can be written as P1 times V1 equals P2 times V2, where the 1 and the 2 represent kind of an initial and a final setting. So the initial pressure times the initial volume will equal the product of the final pressure and final volume. So we'll see that 1 and 2 subscript stuff as we go through each of these 3 remaining laws. The next law is Charles's law. Charles is how we say it in the United States, named for Jacques Charles. Did a lot of work analyzing temperature and volumes relationships to each other. Again, we hold two variables constant. In this case, it's the number of moles and the pressure. When we hold those two variables constant, we can see that the temperature and volume of a gas will be directly related, which means as temperature goes up, so does volume, and vice versa. So as you see in my illustration again, very poor illustration that it is, that's supposed to be a thermometer on the right side of the cylinder. And G, you can see the kind of level of mercury or red dyed alcohol rise from the upper image to the lower image. The temperature goes up and therefore it pushes the little piston, the hat looking thing, up. Think about having a balloon in a hot car. If you leave a balloon in a hot car, it can certainly reach such a volume that it tenses the latex or whatever the balloon is made of to such an extent that it pops. So just kind of think about that. No, we're not really holding number of moles and pressure constant there, but willing suspension of disbelief at this point. The equation we use for Charles's law is V1 over T1 equals V2 over T2, again signifying a direct relationship. Avogadro's law, named for Amadeus Avogadro, who did fabulous work with number of moles and volume and has that fun number 6.02 times 10 to the 23rd representative particles named for him in honor of the work that he did, figuring out that regardless of the volume that we have, 1 mole of any gas will occupy the same volume. We'll get to that a little bit later as well. He realized that if you change the number of moles of a gas, then the volume will increase proportionally. And that is true only when we hold pressure and temperature constant. The formula for it is V1 over N1 equals V2 over N2. Again, a direct relationship is exemplified by that formula. I hope that you notice that the artwork on this slide happens to be an avocado because it sounds kind of like Avogadro. Get it? And it's a darn cute one with those fun eyes, isn't it? Alrighty, next law is Gay-Lussac's law. And Gay-Lussac was another French gentleman who analyzed kind of the opposite of what Avogadro did. Avogadro was Italian, by the way. And Gay-Lussac analyzed pressure and temperature's relationship when we hold number of moles and volume constant. Pressure and temperature are found to be directly related, and the equation is P1 over T1 equals P2 over T2. That horrific, my gosh, that thing is awful. I chose those years ago. Illustration shows us that if we, have a cylinder and we increase the temperature, then the pressure is going to push the little mercury column, which is the gray thing, up toward the atmosphere. So it's going down and then up again around that U-shaped thing. Godly, that's just pitiful. I did fail to mention that anytime we use temperature in gas law problems, unlike thermodynamic problems, we have to use Kelvin. Indeed, we have to use Kelvin because the guarantee of no zero is a pretty powerful thing when we're comparing it to pressures and volumes and number of moles, when it's really hard to measure zero of any of those three. So now you have some practice problems. I gave you 7 practice problems. And what I'm going to do is go ahead and give you the answers. I told you this was going to be short. I'm going to go ahead and give you the answers to those 7. And then what I recommend you're doing is writing down those answers that you hear me give you, or coming back and just listening to them once you've worked out the problems. Again, keep in mind that you have to work in Kelvin temperatures. Keep in mind that we're only at this point analyzing 2 variables at a time. And in one of these problems, you do have to consider that 2 gases were collected in the same space. So it really involves 2 persons' gas laws. So number 1, the answer is 844 millimeters of mercury. Number 2, 5.50 liters. Number 3, 159 torr. Number 4, the first answer is 726 millimeters of mercury for the oxygen in the bottle. And then once it equalizes its pressure with the atmosphere, it will have a volume of 311 milliliters. Told you you'd hear some bells. It's 9 o'clock p.m. You're going to hear lots of bells. Alrighty, number 5, 1.59 liters. Number 6, 4.40 grams. And number 7, 1.97 atmospheres. I think this could possibly be the shortest one I've ever done. I don't know where the original one of these that I did went, but oh well, you've got a new one. And the next one that I need to record will be on combined gas law and ideal gas law. It will be another fairly brief one, but I will do it in a few days. Thanks for listening. Hope you had fun. Bye.